Welcome to Artificial Intelligence Deep Learning and Statistics Amalgamation Incorporation. This is your PhD AI730 Lecture 14, and this is your Professor T. Farid Muhammad. In this lecture, we'll continue our discussions on the topics non-convex optimization that involves objective functions that have multiple local minima, making it more challenging to find the global optimum. Despite these challenges, non-convex optimization is crucial in artificial intelligence, particularly in training deep neural networks, where the loss landscapes are highly non-convex. We will explore various techniques and algorithms designed to navigate these complex landscapes, such as gradient descent, variant stochastic gradient descent, and advanced methods like ADAM and RMS-prob in actual industrial use cases that we have been witnessing or we can dig deep into. Understanding these optimization techniques is essential for developing robust AI algorithms capable of handling large-scale complex problems. By mastering these methods, we can enhance the performance and efficiency of AI models, enabling them to tackle real-world challenges more effectively. So Google DeepMind team faced the challenge of non-convex optimization head-on when developing AlphaFold, the revolutionary protein structure prediction system. Proteins fold into complex three-dimensional shapes determined by sequence of amino acids, and predicting these shapes requires optimizing neural network parameters across a landscape of complex and non-convex that traditional methods would simply fail. DeepMind's engineers had to design specialized optimization strategies that could navigate this rugged landscape reliably enough to produce scientifically accurate predictions. The result was a system that solved a problem that had stumped biologists for 50 years, demonstrating that with the right non-convex optimization strategies, deep learning can tackle problems of extraordinary complexity and real-world importance in fields as demanding as structural biology. So the training at deep convolutional neural networks for facial recognition involves optimizing millions of parameters through a non-convex landscape where multiple parameter configurations can achieve different but locally optimal face detection accuracies. This is another example. Here is a research question for you to ponder upon. How can we theoretically characterize which local minima in deep neural networks provide comparable generalization performance to global minima, and under what conditions are all local minima approximately equally good? So do go on Google Scholar and find the details and see how it works with you. So Microsoft Research has invested heavily in loss landscape visualization tools to understand why certain neural network architectures used in their Azure AI services train reliably while others fail at an unpredictable scale. The researchers discovered that transformer models used in products like Bing's search, ranking, and Azure cognitive services have fundamentally different landscape geometry depending on how attention layers are configured, with some configurations creating smooth navigable terrain and others producing sharp cliffs that cause catastrophic training failures. By visualizing these landscapes before committing to expensive training runs on large computing clusters, Microsoft teams can identify problematic architectures early and modify them to create smoother optimization terrain, saving enormous amounts of computational resources and engineering time. So the researchers visualized ResNet loss landscapes by sampling two random directions from a trained model and plotting loss values, discovering that skip connections create smoother landscape with fewer obstacles compared to networks without shortcuts. Meta's or Facebook's artificial intelligence research team encountered the local versus global minima problem dramatically when training their large language models for content moderation across Facebook and Instagram. Early versions of their moderation to models would converge to local minima that learn to identify obvious harmful content like explicit profanity but completely missed subtler forms of harassment and coordinated inauthentic behavior. These local solutions were mathematically stable and showed good training metrics, creating a false sense of success before real world deployment revealed catastrophic blind spots. Meta's engineers responded by developing an ensemble training approaches and diverse initialization strategies that explore different regions of the parameter landscape, discovering solutions that were far better overall, even if they required significantly more computational resources to find. So, a neural network for medical image segmentation might converge to a local minimum achieving 85% accuracy, while a global minimum exists with 92% accuracy but remains undiscovered due to initialization or optimization algorithm limitations. So now let's look at gradient descent in non-convex settings. Tesla's autopilot team relies on gradient descent navigating non-convex landscape to train the perception systems that allow their vehicles to detect pedestrians, cyclists, and obstacles from camera footage in real time. The non-convex nature of their training problem became dramatically apparent when early versions of their models trained with naive gradient descent would settle into local minima that performed well in sunny California driving conditions but failed dangerously in rain, fog, and nighttime scenarios. Tesla addressed this by carefully designing their gradient descent procedures with specific initialization schemes and learning rate strategies tailored to the non-convex structure of their perception task, gradually developing robust, the modular, robust enough models to handle the enormous diversity of real-world driving conditions across different geographical and weather patterns. So the Training a recurrent network for language modeling uses gradient descent to update embedding and hidden layers weights, potentially settling into local minima where the model learns basic grammar but fails to capture complex semantic relationship. Here is your research question that I would like to pose on you to look at Google Scholar or IEEE Explore. What conditions on step size, momentum, and noise injection guarantee that gradient descent escapes poor local minima and converges to solutions with acceptable loss value in polynomial time? So do look into this and see what you get. Initialization strategies. So OpenAI's development of GPT models demonstrated the critical importance of initialization strategies when training and at unprecedented scale. When the team first attempted to train very deep transformer networks for what would eventually become the foundation of ChatGPT, poor initialization choices caused gradient signals to either explode into numerically unstable territory or vanish completely before reaching the early layers, making training impossible regardless of how long they ran the optimization. OpenAI's researchers developed carefully calibrated initialization schemes specifically designed for the transformer architectures, attention mechanisms and feed forward layers, taking into account the depth of network and dimensionality of each layer. These initialization choices were so important that they became one of the key engineering contributions enabling training of models at scales previously thought impractical. So Xavier initialization for neural network scales initial weights based on layer dimensions to maintain gradient magnitudes across layers, preventing earlier layers from having vanishing small gradients during backpropagation in deep architectures. So the noise effects, it's in reality stochastic gradient descent noise effects is the main topic here. So Spotify's machine learning team discovered the generalization benefits of stochastic gradient descent noise when building their music recommendation system that serves hundreds of millions of users globally. When they experimented with using very large batches to speed up training on their massive listening history dataset, they found that the resulting models were excellent at recommending music similar to what the users had already heard, but surprisingly poor at surfacing genuinely novel music that users would enjoy. The large batches reduced gradient noise so much that the optimizers found sharp narrow minima and memorized popular listening patterns without capturing the deeper structure of musical taste. By reintroducing noise through smaller batches, Spotify's models found flatter solutions that generalized better to unusual or emerging artists, directly improving user satisfaction and engagement with new music discovery. So training BERT language models on massive text corpora uses mini-batch SGD where gradient noise from different text samples helps the optimizer avoid overfitting to specific linguistic patterns and find more robust representations. Here's a research question for you. How does the variance of gradient estimates from different batch sizes quantitatively affect the probability of escaping different types of local minima? And what is the optimal noise level for different landscape geometries? So the batch size control the trade-offs between gradient estimate accuracy and computational efficiency per iteration. With large or larger batches providing more accurate gradients but fewer parameters updates per epoch and less stochastic exploration. Training ImageNet classifiers with small batches 32 images produces noisy but frequent updates, enabling escape from sharp minima, while large batches 8,192 images give stable updates but may converge to sharper, less generalizable solution. And the rate decay schedules. The learning rate decay reduces the step size over time according to the predefined schedules like exponential decay, polynomial decay, and step decay, permitting large initial steps for rapid exploration followed by small steps for precise convergence. Training GPT models uses cosine annealing, where learning rate follows a cosine curve from a maximum to near zero over training, enabling aggressive early learning while ensuring stable convergence to refined parameter values. The research question for you to ponder upon is: what theoretical principles should guide learning rate schedule design for different problem structures, and can we prove convergence rate improvements for adaptive schedules compared to constant learning rates? So the warm starts periodically reset the learning rate to its initial high value during training, permitting the optimizer to escape from potential local minima and explore different regions of the parameter space before. Neural architecture search uses stochastic gradient descent, which warm restarts to train thousands of candidate architectures where periodic learning rate increases help each architecture escape poor initialization and reach better solution faster. So the warm restarts by itself is in itself a whole area of research. The example I can share with you, which I have faced them utilizing, is Hugging Face, the company whose open source model library powers a significant fraction of real world natural language processing applications. Adopted warm restart strategies after discovering that many of their pre trained language models were converging to suboptimal solutions during fine tuning on specific tasks. When companies using their platform fine tuned models for specialized tasks like legal document analysis or medical record processing, the optimizer would quickly settle into a local minima that adapted superficially to the new domain without truly capturing its specialized vocabulary and reasoning patterns. By implementing cosine annealing with warm restarts in their training recipes, Hugging Face enabled the optimizer to periodically explore new regions of the parameter space before resettling, finding solutions, and adapted more deeply and robustly to specialized domains. This improvement had significant downstream impact for the thousands of companies relying on their platform for production natural language processing. Momentum methods. So, DeepMind's reinforcement learning team found momentum methods indispensable when training AlphaGo and its successors to play the board game Go at superhuman levels. The policy and the value networks at the heart of these systems faced extremely non-convex loss landscapes, where naive gradient descent without momentum would get trapped in configurations corresponding to competent but ultimately limited playing strategies. Momentum allowed the optimal optimization to build consistent improvement trajectories through the parameter space, maintaining progress through plateaus in the loss landscape where the gradient signal temporarily weakened during training. Without momentum, early AlphaGo training runs would stagnate at performance levels equivalent to strong amateur play, but with appropriately tuned momentum, the same network continued improving until surpassing all human players, demonstrating how this seemingly simplified algorithmic addition can make the difference between merely good and genuinely revolutionary performance. So, can we prove that momentum methods achieve faster convergence to approximate local minima in non-convex problems compared to vanilla gradient descent, and what momentum coefficients are provably optimal? That's your research question. The Nesterov accelerated gradient, the training video classification. Networks uses Nesterov acceleration to handle the high dimensional temporal feature space where look ahead gradient evaluation provides more accurate descent directions through complex spatiotemporal loss landscape. So, Adagrad optimizer training word embedding for natural processing uses Adagrad to handle the extreme frequency imbalance between common words like the, requiring small careful updates, and rare words like serendipitous, requiring larger exploratory updates. This is your research question here. How does Adagrad's aggressive learning rate reduction affects convergence in deep networks trained for many epochs, and can we modify the accumulation to prevent learning rates from decaying to non-zero prematurely. So the RMS prop optimizer, the training recurrent neural networks for speech recognition uses RMS prop to handle the widely varying gradient magnitudes across different time steps, automatically scaling updates to prevent exploding or vanishing gradient problems. The Adam optimizer details. So the training transform models for machine translation uses Adam with standard hyperparameters. Beta 1 is 0.9, beta 2 is 0.999 that work reliably across different language pairs, eliminating the need for extensive learning rate tuning that would be required with vanilla SGD. Now, that is something that I suggest you to conduct research in a little bit more depth, because I have seen OpenAI's training for GPT series for language models when I was part of the research group at UNC Charlotte, which powers, so this technically OpenAI is a thing that powered ChatGPT and underlying technology licensed to Microsoft later on for Copilot products, uses Adam as a foundational optimizer precisely because of its robustness across the unprecedented scale of their training runs, because Microsoft is pretty much everywhere in our industry. Adaptive learning rates. I would suggest you to conduct adaptive learning rates research by pondering upon under what conditions do adaptive methods outperform carefully tuned SGD, and can we predict from dataset or architecture properties which optimizer family will be more effective for a given problem. Gradient clipping. Training long short-term memory networks, LSTM, for video captioning uses gradient clipping at threshold 5.0 to prevent occasional extremely large gradients from sequences with unusual temporal patterns from destroying previously learned parameter values. The second order methods, so the research question I would pose on you, so it'll be better for you to conduct research in this area. Can we develop scalable approximations to second order methods that capture essential curvature information while remaining computationally tractable for billion parameter models, perhaps through block, diagonal, or low rank Hessian approximation? So second order methods is also an area that I would suggest you to conduct a little research. I have once read about Waymo, the Alphabet's autonomous driving subsidiary, explored second order optimization methods when training the perception and prediction models that must reliably identify and predict the behavior of other vehicles, pedestrians and cyclists in real time. So that's like Tesla. Their engineers investigated quasi-Newton methods for training specialized safety-critical components of their system, where the superior convergence properties of second-order methods could reduce the risk of models getting trapped in local minima and with dangerous blind spots, while the full second-order approach remained impractical for their largest neural networks. Waymo's research team developed log diagonal curvature approximations targeting the most safety-critical layers of their architecture, achieving improved convergence reliability for the components most directly responsible for detecting rare but dangerous edge cases like partially obscured pedestrians or unusual vehicle behavior. This targeted application of approximate second-order information improved the robustness of their most critical safety systems. Natural gradient descent. So training probabilistic models like variational autoencoders or VAE uses natural gradient methods to ensure that parameter updates produce controlled changes in the output distribution, preventing mode collapse and maintaining diversity in generated samples. So that I have witnessed something that I'd like to share with you. That researchers at Preferred Networks in Japan, they developed AI systems for industrial robotics and drug discovery also. The Preferred Networks adopted natural gradient methods when training robotic control policies that needed to transfer reliably from simulation to real physical robots. Standard gradients descent uh, produced policies where seemingly small parameter changes caused dramatic shifts in the behavior, making the training process unstable and transfer from simulation to reality particularly unreliable. So the future optimization, the future optimization in reality is something that I like to share with you. That where they are heading, the DeepMind's development of learned optimizer systems, most notably in their work on training neural networks that themselves serves as optimizers for other neural networks, represent perhaps the most radical future direction being actively pursued in industry today. So the emerging research explores learned optimizers that use neural networks to predict optimal update directions, Bayesian optimization for hyperparameter tuning, optimization under distribution shift, and theoretical understanding of why deep learning optimization succeeds despite non-convexity. Meta-learning systems train LSTM, long short-term memory networks to act as optimizers, learning from experience across thousands of optimization tasks to predict better update rules than hand-designed algorithms like Adam or specific problems. Happy learning. See you in the next lecture.